Okay, Lagrange multipliers with two constraints. Oh my. Now, in this situation, we're going to assume that W has 3 inputs and 1 output. So that doesn't really graph to be anything in three-dimensional space, does it? So suppose W equals f of x, y, z has two constraints. So one constraint is g of x, y, z equals c. That's a surface in space, isn't it? It's an implicitly defined function of x, y, and z. Likewise, so is, that's where c is a constant. H of x, y, z equals k, k a constant, is also a surface in space. And what we're really saying is the domain for W, the x, y, and z values you're allowed to plug in, have to lie both on the surface G, given by G, and the surface given by H. So both of those constraints must be satisfied. And by the way, how do two surfaces intersect? They're going to intersect in what kind of object? A curve. So those two surfaces, G and H, where they intersect, the intersection curve, that's your domain for F. Does that make sense? Can you kind of picture that? I can try and help you picture that. Okay, so how could I picture that? We could picture maybe, let's see, maybe I'll draw it this way. Okay, so there's kind of, picture a blanket frozen in space maybe. Okay, so that's G. We'll call this one G, the guy in blue G. And then maybe you have H coming up like this and intersecting. Okay, coming like this. It's not a plane, it curves. It's just nice and smooth, especially if you're zoomed in on it. And then this guy will connect back here. Maybe it looks better if I don't let them connect. I'll do it dotted. Okay. So somewhere back here. And so you're looking at part of H, that's in red, the surface in red, and part of G, the surface in blue. Where do they intersect? Maybe along an intersection curve, right? So that intersection curve is your domain. Does that give you an idea? Okay, then the domain of F is on the curve of intersection of H and G. That's what we just pictured. And then if F of x naught, y naught, z naught is an extremum, either an absolute maximum or an absolute minimum on that constraint curve, then it turns out that del F evaluated at the critical point is x naught, y naught, z naught. Del F evaluated at x naught, y naught, z naught, turns out it's in the plane created by del G at x naught, y naught, z naught, and del H at x naught, y naught, z naught. To give you an idea of why that's true, let me draw del H as maybe a vector right here. Whoa, that's thick. Okay. That's fine. So I'm trying to draw it so that it looks, so this guy in red is del H. So del H should be normal to its level surface, which you can think of as H of x, y, z equals k or whatever it was. Okay? So that del H, that vector at x naught, y naught, z naught, at the critical point, we're assuming that there's a critical point on this curve of intersection right there. So that's x naught, y naught, z naught. That's pretty important you understand that. Or maybe a local extremum occurs there. We'll just make that assumption. So it's not only a critical point, but there's definitely, when you plug that critical point into F, it's going to be either an absolute max or absolute min. So we learned that last time that del H should be normal to its level surface, which you can think of H, the function H equals K, as the level surface of H of x, y, z. So that's what I'm trying to draw there. Does that seem somewhat reasonable? And then likewise, del G, which I'll draw with the thick blue color, I guess, del G should be normal to the surface G. So that would actually look maybe like that. Well, wait a minute. Maybe more like that. So if a contour of G looks something like this, then we've got a right angle here. Okay? And it's reasonably easy to prove that del F evaluated at x naught, y naught, z naught will be normal to that curve of intersection, that constraint curve. And in space, there's lots of ways del F could be normal to that curve in purple, right? So del F will be in green. Okay, where could del F be? As long as it's normal, it could be anywhere in a 360-degree rotation, right? But as long as it's normal to the curve in purple. But my hand-wavy argument is if all three, so this is del F, and it will be normal, I could put it anywhere in a 360-degree circle, but it will be normal to that constraint curve in purple there, that intersection curve of the surface H and the surface G. And so my argument is, if you looked at this, if you rotated it to the side, the blue vector, the red vector, the green vector would all lie in the same plane. Does that seem reasonable? As long as you believe del F is normal to the constraint curve. And by the way, this guy in blue is del G. I didn't label that. So would you agree they lie in the same plane? That's important for the method. Okay. So three vectors that lie in the same plane, well, using the triangle law, you could then create a scalar multiple of del G and a scalar multiple of del H such that del F is the sum of those two scalar multiples. So if you believe that all three of these vectors are in the same plane, then by the triangle law, there's going to exist two scalar multiples, two Lagrange multipliers, such that del F should equal, let's say, lambda del G plus, and this is all happening at the critical point, mu, that's a Greek symbol too, looks like a U with an extra tail, mu del H. Okay? In other words, you should be able to extend this the right length, extend this guy the right length, so that when you add tip to tail and connect, you get the vector in green. Okay? That's the triangle law. And that we can use to create a system of equations, just like we did for the other case where we had one constraint, and the method pretty much looks the same. Okay, so that's a little hand-wavy, but hopefully you bought that.